So, scale analysis. Is the act of replacing this system of equations with a system of algebraic equations. From partial differential equations to algebraic equations. In other words, statements of order of magnitude equality between terms. In other words, statements of equality between two scales. So scale of the left-hand side, the same as the scale of the right-hand side. But this is already abstract, so let me be more and more open about it. Now, scale, the word, comes from the Latin word for ladder or staircase. Meaning that the altitude here is different than here. So there is a scale of sizes, of numbers. Here it is. For anything that you measure, you can list all these. You can actually scribe. That's what abscissa means. It means, abscissa means cut, feminine, a line that was cut. Linea abscissa, here, cut. And this is size 1, size 10, size 100, and so on. If this is the scale of length, or lengths, in other words, these numbers represent meters, then the entire arpeggio is one dimension. Dimension is called length, not to be confused with mass, or with velocity, or with temperature. Those are dimensions. So there's one dimension. One dimension. Not to be confused with the distribution, which is this ladder, or the scales, all scribed on this particular line. So scale represents order of magnitude. Actually, it means magnitude. Because clearly you will not confuse 100 with 10. You see, 100 is bigger than 10. Which one is weird in this comparison? The size 3. Size 3 is kind of both male and female, okay? This or this, you see. But that's freedom for you, because you have a formula that has this factor of 3. If you like 1, or whatever, if you like the simpler number, then you can opt for that and you're still okay. So scale represents order of magnitude. And the simplest problem that I invented in order to teach how to go from partial differential equation to an algebraic equation, and to show the power of this method, is the problem of the immersion heating of an object. This happens in metallurgy all the time. what do you call this process where you heat the steel red hot and then you plunge it in water? Quenching is one. Thank you. Is one example. I don't do that. I spend a lot of time cooking. The boiled egg. the egg is not boiling. It is the water around it that's at constant temperature because of boiling. And the egg in the beginning is a blob of lower temperature, which then is heated over time by sudden immersion. So the problem is the following. I have an object, think of it as a slab, meaning it's two-dimensional, but what we see is the cross-section that matters, is this slender rectangle, slender enough for us to consider it as one-dimensional, stretching from, meaning in the x direction, from minus thickness divided by 2 to plus thickness divided by 2. So the thickness of the slab is capital D. So there's just one direction called x, over which the temperature varies. And I'll plot the temperature in this direction. Outside, the temperature is uniform, say the boiling water. In the case of quenching, the water is tap water is cold and the body is very, very hot, but it's the same problem. It's the problem of immersion, in this case heating, versus immersion cooling. And so the bath temperature is T infinity, and the original temperature of the solid is T0. So the original temperature distribution is this one. Okay. I said solid because of those examples, even though the inside of the egg is really not solid. It becomes solid soon enough through this so-called boiling. And the temperature of the, by the way, before I continue, solid means that nothing moves. No fluid motion, no enthalpy and anything like that. No U and V, 0. So this is a problem of heat conduction. Heat conduction is the early version, the first child that came out of these French mathematicians. So solid means heat conduction or heat diffusion. In that limit, the only equation that survives from this panel is the energy equation with no convection on the left, but with, well, no convection except this dt, the time. And on the right, this Laplacian will reduce itself to d2t dx2, because there is only one direction in which the temperature varies. So that means that the energy equation is the temperature, the time, equals alpha, because I've divided it by rho Cp, and then d2t dx2. You've been taught, it's been drilled into you to to make a sketch and identify the boundary conditions and, of course, the initial condition. The boundary conditions is already our graphic. They have to do with the fact that there are two boundary conditions. The first one is that on the center line, meaning the center line is a plane of symmetry. Because of symmetry, the temperature distribution, let's sketch one of them. The temperature distribution later is like a meniscus, must have dt dx equals 0. And then the second boundary condition is that on a surface, either left or right, so at x equals d over 2, the temperature is the bath temperature. And then there's an initial condition, namely that at time t equals 0, the temperature everywhere in the solid is T0. So this is the mathematical statement that you've been taught. This, by the way, is a problem that can be solved exactly. It's one of the first problems in a course on conduction. But I'm using it to teach not poor man's version of the solution, the version that belongs to the clever person who doesn't have time to split hairs. And it has to do with the fact that, first of all, what is the problem? Really, put yourself in the shoe of the metallurgy type, you know. What's your problem? Quenching. You know, you don't have time forever to do the quenching, or for that matter, to boil the egg. The problem is to predict the time of quenching or the time of egg boiling. So you could move on to boiling the next egg and the next egg. So, in other words, you are challenged to figure out, meaning with the eyes of your mind, what happens inside the object. Well, what happens inside the object, I already sketched one photograph of what happened in my mind, but I'm going to draw it much bigger here. If the distribution of temperature was this way, and with, of course, the plane of symmetry right there, in the beginning, where there is an instant clash between hot and cold, the solid that is heated first is the one that's touched first. And that means that the temperature that used to be top hat will acquire rounded corners. Later, beginning with chapter 2, we'll call them boundary layers. And now you get the idea that boundary layers, even though they are the creation of Prandtl in the fluid flow, year 1900, had been in play in conduction already in the minds of these people who created the beginning of the field of heat transfer. And then time increases, meaning time passes, because time is the observation that things have changed. And the feeling with the perception of hotness penetrates. And there comes a time where the center feels the heating effect. That time, in what I'm going to show you next, is called characteristic time, or thermal diffusion time, or time of thermal diffusion penetration. So diffusion time. I mean, after this time, clearly the temperature continues to rise as the solid stores more and more of the energy that's being piped into it, but it stores that energy at a decreasing rate. Meaning that what's interesting about the process is the beginning, because it's never like the first time. After this characteristic time, things are not changing much. So every immersion heating and cooling process has a characteristic time scale about it. What is that? Because that time scale defines the process, the technology. Okay? So this is the question. And next is, here's the answer, which I happen to know. I already told you that my mother told me, talk about things you know, not about things you don't know. But then I figured out that the better version of that in this business called academia is to ask questions to which you know the answer. If you have questions that have not been answered, keep those to yourself. Yeah, make a problem, solve it, and publish a paper about that question that no one has come up with. There are a bunch of people, in fact, there are papers published, unanswered questions in fluid mechanics. Yeah, brilliant people, and they go, they spell out these questions that occur to them, but they think that they have not been answered, you know. And well, the joke is on them, because a lot of those questions that are still unanswered have been answered. But if they're good enough to be spelled out, maybe the author of the manifesto should keep quiet and go about answering those questions himself. All right, so what is the order of magnitude of this quantity? A number of seconds or minutes. Well, I should get it from the only equation that exists. So what is the order of magnitude of this term versus that term? So the left-hand side, which is the partial of temperature with respect to time, during the life of the process. And the process that concerns me is from t equals 0 to t of the order of this characteristic time. After t sub c, the story gets boring, okay? And, well, here we go. This sign means of the order of, which means I'm positive, I'm confident that that is the size without a factor of order 1. In other words, it's 1 kilogram or 2 kilograms. That's the order of magnitude 1 kilogram. All right, so in this case, what is that? Well, imagine integrating this left-hand side during the duration of the process. In other words, the temperature at time t sub c minus the temperature at t0 divided by the time excursion, which is from t sub c, from 0 to t sub c. See? From 0 to t sub c. And first of all, the downstairs is the object of the game, my unknown. Upstairs is the temperature scale between heated solid and an unheated solid. I'll call that delta T. So this is the algebraic expression for the left-hand side. For the right-hand side, I behave as if I know nothing except what I did here. So right-hand side, I am behaving religiously. I just look at the right-hand side and I do this. Here's the right-hand side, alpha d2t dx2, which of course is alpha partial with respect to x of the derivative d dx. Next, I leave the front intact. The order of magnitude of the guts, the temperature gradient from side to the interior is obviously delta T over the distance of thermal penetration, which is capital D divided by 2. And the order of magnitude of the step executed in the, meaning step in my mind, in the x direction is d over 2. I should have put of the order of here. And so the conclusion at this stage is that the right-hand side is of order, I forgot to write alpha again, alpha, and then delta T over d/2 squared. In fact, I'll continue this argument here. So I'm left with, from the left-hand side, delta T over T sub C of the same order as alpha, delta T over d/2 squared. In an order of magnitude sense, and with great confidence, because the problem is that simple. This dropping of the delta T happens regularly in convection, and you end up with the conclusion that the unknown, the order of magnitude of this, let's call it cooking time, is b squared over 4 alpha. Let me see if I get it right. Yeah. If you go into the problem that I erased has been solved exactly according to mathematical analysis. All the plots, all the numbers that came from that solution are of this order of magnitude. And this is the formula that's worth remembering. For example, when you're in the kitchen wondering how long you should cook a roast, you know, and the instructions in the cookbook tell you about a roast that of a particular size, meaning a particular thickness, but your roast is not of that size, then you can use this formula to translate the instruction from the cookbook to apply to what should go on in the oven that you use. In the kitchen, the cooking in the oven is not by immersion. That applies to the boiling egg. The outside of the body of meat is experiencing convective heat transfer, which is something we'll deal with a little bit later. But I give you the example of, the of the importance of a simple formula, it empowers you to scale up or scale down an application. This formula is valid for tiny things, small eggs, and big eggs. And each application or invocation of the formula tells you how the cooking time changes from one application to the next. Speaking of unsolved problems, you'll run into geniuses who will tell you that the problem of scaling up and scaling down has not been solved. It has been solved if you know scale analysis, because scale analysis is about figuring out the scale, not the number, but the formula. How things change, meaning in this case size or time, that's another kind of size. In this case, how they change with the size of the object. Another way to skin a cat is to rewrite this as d over 2 of the same order as square root of alpha t. And the d over 2, because you're going to hear people use these words. D over 2 is called thermal penetration depth, because to go from the side to the center, the heating penetrates the body. So thermal penetration distance. This T sub c, by the way, is also known as diffusion time. Meaning thermal diffusion time or conduction time. And so I'm teaching you jargon that goes with the field of convection. If you know the terms, it's like knowing the jokes in the locker room. You belong there, you see, and you're not wasting your time. You're not asking, what do you mean by that? So that's the so that's scale analysis. Before I say something else, of course, scale analysis, all of this, should not be confused with dimensional analysis. Dimensional analysis is knowing the difference between length and mass and time and temperature. Those are dimensions. Scale is to know this arpeggio of values of one dimension, called length, in this case called time. Short time, long time, and how those marks on the axis of sizes depend on the size of the object. And that's why probably the title for this lecture is cooking time or quenching time, or how not to overcook something or undercook something. Is that important? Okay, I call it Venkitu because that sounds closer to my sound.
What is alpha?
Alpha is the thermal diffusivity. Alpha is shorthand for rho over C, K over rho C sub P. K is the thermal conductivity. C sub P is specific heat at constant pressure. So specific heat at P constant. P constant has nothing to do with anything. This is just a number in a table. P constant refers to the experiment in which C sub P is measured. But once measured, this number is known and tabulated. Something else, many people make the mistake of confusing specific heat with heat capacity. Heat capacity is the product. And usually it is a capital C sub P. I don't use the heat capacity, but you should know the difference between those two, meaning between those two terms. They refer to the same formula, this formula for the specific, in this case, for the thermal diffusivity. So alpha is thermal diffusivity. Okay? Yes?
So D here, is that the width of the egg?
Louder?
D, is that the width of the egg?
Yes, yeah. D is the distance from minus D2 to plus D2.
So if I had like a steak that I was cooking in boiling water for some reason, and then I took that and I like had the same size steak but made a bunch of cuts in it to increase the surface area, wouldn't that be the same D but cook faster?
It would, but in that case, your cuts would be transversal, meaning they will be collinear with D. And then you end up with a two-dimensional object, a slab with striations develops two-dimensional. It's in the simplest two-dimensional structure. Is not what I sketched here. But since you bring up this thing with the steak, which is of course I know really well because I cook all the time. There was a student. I had him in the late 1990s, Alex Fowler, now a big professor at the university northeast of here. And we're talking just like this, you and Adrian, about cooking a piece of meat, you know. And I don't know who said it first, but that particular slab, as you cook it, shrinks, meaning the D there is a function of time because it is volumetrically a function of temperature. So we wrote a paper, the effect of shrinking on cooking time. We did, and submitted it to the ASME Journal of Heat Transfer. Back then it was the Olympics of heat transfer. And the editor did not even review the paper. He thought it was a joke. We laughed the hardest. We submitted to another journal in Europe, and it got published. Because the meat shrinks by 25%. Go ahead and grill a steak. You'll see it. In fact, this is how you can tell that you've passed this characteristic time, is when the heating has penetrated the object. You see it. In fact, this is how the talented cooks know when the steak is at the right doneness. They look at the shrinking of it. They don't stick a thermometer in it. They don't have time for that. Get it? So I'm glad you bring it up, because the story I just gave you, spontaneous, is about the importance of connecting this verbiage, which is abstract even if it is the simplest technique, connecting it to what you know, to what you felt. Not only here, but in the village. Wherever you come from, you've had contact with heating and cooling, and with air blowing, hot air, cold air,